Happy day and welcome everybody. We're talking about Q today, okay? And so what is Q? Well, Q is called the reaction quotient. And so what Q helps us predict is as long as we know what K is, which is our equilibrium constant, we can compare Q to K and we can figure out what direction our reaction is going to proceed in. We know that reactions want to come to equilibrium. Equilibrium is kind of your comfort zone, right? That's what we've been calling it. So that's kind of like coming back home or coming to home base. So what we want to do is we want to predict the direction of a reaction, so we can throw in random concentrations, but if we throw in random concentrations, we cannot call it K because it's not at equilibrium. We call it Q. Okay, so that's kind of the major difference between the two. So it says our next focus is using what we know about K to help predict the direction of a reaction when we throw in various concentrations of substances. When we substitute random concentrations into the equilibrium constant, the result is called the reaction quotient, or Q. Comparing this result to K, the equilibrium constant, we can predict which reaction it will proceed, just like I was saying. If the value of Q is products over reactants and it's less than K, then remember what we do here, we're going to do the alligator mouth, and so I'm going to make some alligator sounds here, but we're going to go in the direction, wherever the mouth is of the alligator, that's heading towards the products. And so then the question is, well, what does that mean? So I'm going to tell you in just a moment here. And so you want to reach equilibrium. The system is going to shift towards the products, thus increasing the value of Q. And as you increase the value of Q, you'll eventually get to K. So that's what your goal is to try to reach K. If the value of Q is greater than K, then the opposite is going to happen. So in that situation, if Q is greater than K, we're going to shift backwards towards the reactants. And thus, your products will be consumed and you're going to make more reactants, decreasing your value of Q. Okay, so again, Q is equal to products, concentration of products over the concentration of the reactants. So if, let's say, we ended up calculating it and we figured out that Q was equal to, I don't know, let's use the number 1, for example. And we knew that for our reaction, K should be equal to 100. Well, in that case, I know that what I need to do is Q needs to increase in products in order for this number 1 to get bigger. And so I'm going to form more products, meaning I'm going to add on my product side until I get to K, and then the reverse happens if Q is greater than K. All right, so let's take a look here, and so this box kind of just goes over what the situation would be and what would happen to it. So if Q is equal to K, your system's already at equilibrium. There's no change. So on your change step, if you were doing an ice box, for example, there is no change then. Q is equal to K, and your equilibrium concentrations, you're done. If Q is less than K, then your system's going to go forward. What does that mean? Well, that means that if I have A plus B yields C, for example, then that means that in my change step, I would be adding on my product side and subtracting on my change step for my reactants. If Q is greater than K, then that means that my reaction needs to go reverse, okay, which is kind of weird, but it happens. And that means that I'm going to have to favor my reactants. So that means I'm going to add on my reactant side and I'm going to subtract on my product side, okay? And again, that's kind of strange because usually you don't lose products, but it does happen because sometimes they'll even tell you that you charge your flask with products, which is really weird, but it does happen, okay? All right, so let's take a look at question 20 here, and it says, for the synthesis of ammonia, we're going to make ammonia. The equilibrium constant is 6 times 10 to the negative 2. I always like to write it in normal form, right? So that's 0.060, no units. And it says predict the direction in which the system will shift to reach equilibrium in each of the following cases. Okay, so this here, 0.060, is actually my K value. So this is equal to K, capital K. All right, so before we start, we need a reaction. So what is our reaction? Well, we're synthesizing ammonia. So I know I need to make NH3. What does it take to make it? Well, pretty easy, nitrogen and hydrogen. So I know I'm going to need nitrogen gas and hydrogen gas. Let's balance our equation. So I can see that I'm going to need 2 nitrogens to balance that out, and then it makes it 6 hydrogens. So I need a 3 in front of there. Okay, now that I have this, I can write my expression. So my expression is K, or Q, right, is equal to concentration of NH3 squared, my product to the second power, divided by N2 to the first power, and H2 to the third power. Okay, so now what I need to do is figure out, these are random concentrations in A, B, and C. So let's do A down here, and I'm going to figure out what Q is, because these are not at equilibrium, so I need to actually work my calculations out. So all I'm going to do is my NH3, which is 1.0 times 10 to the negative 3, I'm going to square that, divided by N2, which is 1 times 10 to the negative 5, and then multiply that by my H2, which is 2 times 10 to the negative 3, but don't forget, that needs to be cubed. All right, so let's go ahead and let's plug this in and check to see what we get. Did you get 1.3 times 10 to the 7th? Remember, no units, it's Q. Okay, so what we're going to do is we're going to compare Q to K. So we said that K is 0.060. So I've got Q as this number here and K as 0.060. So I know that Q is actually way, way, way bigger than K. And if Q is greater than K, which direction does it go? So are you thinking alligator mouth? It's going to favor which side? Well, it's going to go backwards and favor the reactants, okay? So remember, it's wherever the direction is of the mouth of the alligator. So this is going to, and I'm just going to say it's going to shift left. Let's keep it simple, and let's just say it is going to shift left. When does it stop shifting left? It stops shifting left as soon as it reaches equilibrium, and your value is equal to 0.060, okay? So shifts to the left. Okay, so what I want you to do is I want you to calculate B and C. You can simply plug it into your calculator. You don't have to write it all out. Let's see what answers we get. We'll come back and figure out what's happening to the reaction when we alter the equilibrium. Okay, so when I calculated the value for B, I got 6 times 10 to the negative 2, which is exactly the same as K. So if Q, and significantly, so if Q is equal to K, there's no shift. You're already at equilibrium. So therefore, we are already at equilibrium concentrations, and we're done, okay? Now for C, I know that Q in this case, if it's 10 to the negative 3, that's 10 to the negative 2, Q is less than K. And so if Q is less than K, now where's my mouth going? My mouth is actually going towards the products, so I'm going to say that this is going to shift to the right, again, until equilibrium is established. And so I'm going to increase my products in that situation until my numerator is bigger, right? It's going to, and as your numerator gets bigger, your denominator gets smaller. Your reactants are turning into products. Okay, so that's kind of what is happening. All right, so let's go back and let's take a look at question 6 now. I want you to know a problem like this would be extra credit. Not the setup of it, okay? So the setup of it is fine. It's just the fact that we would actually need the quadratic, and I'll show you the difference. I want you to see the difference because you will not need the quadratic for any of the questions that they're going to ask you on the AP exam. But I want you to be able to see it and be able to solve it anyway, okay? So in this situation, I have my reaction. I always like to box in my reaction. And so it tells me that the equilibrium constant is 100. That's my value of K. So suppose that the HI is 0.5 atmospheres. Oh, they're giving me pressures, by the way. The H2 is 0.01 atmospheres, and the I2 is 0.00500 atmospheres, and they're mixed in a 5-liter flask. Okay, now, since they're giving me pressures, I actually am not calculating molarity. So they gave me the 5-liter flask, but it really doesn't even matter, okay? So that's not going to make a difference. Calculate the equilibrium pressures of all species. So I need to know the equilibrium pressures for all of them, which probably means none of them are at equilibrium. And it says that they're just mixed. So just mixing them means that this is initial. I don't know what they are at equilibrium yet, which means I'm going to need an icebox, okay? All right, so what do we do first? First thing we do is we set up and we write our expression. So Kp in this case, because it's pressures, And so I'm going to do my HI. So I'm going to do the pressure of HI squared divided by the pressure of H2 times the pressure of I2. All right, so I have my expression. I also know that my K is equal to 100. So let's just go ahead and fill that in since I already know it. And again, I know I'm looking for my equilibrium values. Okay, so let's write our equation here. I've got H2 plus I2 yields back and forth 2HI. And so now I am going to do my little dotted line here. And we've got I, C, E for icebox. Okay, so remember I's initial, C is change. This is where your stoichiometry works. So CH and change, CH in stoichiometry. And then my equilibrium values. Okay, so I know initially what I have. So my HI is at 0.500 atmospheres. My H2 is at 0.0100 atmospheres. And my I2 is 0.00500 atmospheres. Okay, so now I need to figure out what's happening at my change step. Well, unfortunately, they didn't give me anything else. And if they don't give you anything else, guess what we use? We use X, okay? So I'm going to use my ratio. So remember, this is where my coefficients work. So I'm going to call this one X, I'm going to call this one X, and I'm going to call this one 2X. Okay, now, the only thing is I don't know what direction my reaction's going, okay? I really don't. They didn't say anything about it. I have to figure it out by using Q, okay? So what I'm going to do is kind of a little bit of a side note here, right? So I need to figure out what Q is. So Q I know is products over reactants. So, and I'm going to use my expression. It's the same expression as K. So I'm going to do 0.5, and I don't need the zeros. I really just want to figure out if it's greater than or less than K. So 0.5 squared divided by 0.01 times 0.005. Okay, so let's calculate it and see what we get. Okay, and I got 5,000. I can see that my K is equal to 100. Okay, so we've got Q as 5,000 and K as 100. Well, that means that Q is greater than K. All right, so if Q is greater than K, alligator mouth going backwards towards the reactants. So that means it is going to shift left. Okay, what does that mean? Well, shift left, that means that I'm actually going to add on my reactant side. So that's a plus, and that's a plus, and that means that my products must be decreasing. Okay, so let's fill this in then. And again, just for the sake of math, I know I need 3 sig figs in all of these, so I can come back and do 3 sig figs after. So I'm going to call this 0.01 plus X. I'm going to call it 0.005 plus X and 0.5 minus 2X. All right, so now that I have my equilibrium values, well, now I can plug it into my expression, okay? And then I can solve for X. So I've got 100 is equal to my HI squared, so 0.5 minus 2X squared, divided by my H2, which is 0.01 plus X, times 0.005 plus X. And now I have this set up where a lot of your calculators, you can plug this right in and be able to solve for X using your graphing calculator. Okay. So I've got some tips on here on the quadratic and how to solve for X. So the fast way is, and this is something that we could use, using the problem that we just did. You have this right here, and it says you do not need to solve for X any further if you have a graphing calculator, okay? And so depending on whether you have a graphing calculator or if you have an Nspire, this is kind of the way that it works. And so you can try it out and you'll end up figuring out that X is equal to 0.035 in both situations, okay? Now the long way of doing it, the algebraic way of doing it is you actually algebraically get it in the form of the ax squared plus bx plus c equals 0 form. So you get your x squared all on one side, and then your x, and then your numbers, and then you set that all equal to 0. And when you do that, you would actually get this right here, 96x squared plus 3.5x plus a negative 0.245. And once you have this, Now you can use the quadratic, negative b, plus or minus square root, plus or minus square root, b squared minus 4ac, b squared minus 4ac, all over 2a, all over 2a, or whatever you've used to memorize the quadratic. Again, you're not going to need to do this, okay? But just nice to be able to see how it works and what the difference is. And so again, you can get two values of x when you do this. So remember, you get a positive, negative. One of them's negative, ignore it. You would only use the positive number, which is the 0.0354. That's the one that makes sense. And you would get the same answer again, whether you graphed it in that way or not, okay? So you get the 0.0354 basically as your answer. Okay, so let's come back. And so for x, we got 0.0354. So I would have to use the quadratic using the quadratic or graphing, using a graphing calculator. You would get that x is equal to 0.0354. And so once you know what x is equal to, now you come back and you plug it in for each one of these. So this is 0.0354, 0.0354, and 0.0354 for x. So let's go ahead and plug these in and figure out what our equilibrium concentrations would be for each one. Hopefully you got the same answers that I did when you plugged it in, 0.01 plus x, and that your units are actually in atmospheres because this is pressure. And then the other thing I wanted to mention is do not change your K from, like, let's say KP to KC, or if you were thinking like, was this KC, unless you're told, okay? So if you're told it's KC and that you're given pressures, then you'll want to do that switch on that equation. Otherwise, don't do it. So just as a quick little recap as to why we did this, so you can see here that when we look at the equation over here, right over here, I can see that there's really no other way to simplify this besides doing this algebraically and foiling, okay? And so it's quite a challenge, right? And you won't see, again, you will not see problems like this on the AP, but I just wanted to show you what the difference is. Versus if you were looking at a problem where the normal way that the AP would have you do this, if you were using X, is they're going to make it so that both of the reactants are the same and your products then are the same, for example. And so both of them are squared, so all you would have to do is square root both sides, and then the algebra is pretty easy. You don't have to worry about using the quadratic, okay? So hopefully that helped. Happy day to all of you, and hopefully you can do some of these problems on your own now.